Good day, everyone, and welcome to our webinar on Advances in Concrete Technologies towards Low Carbon Sustainable Concrete. Today, we are all privileged to have with us Professor Priyan Mendis, who is a world-renowned expert in this field. So just before we start, let me give you a very short introduction to SDI and also give an introduction to our resource person today. So SDI is a state-of-the-art education firm focused on providing high-quality engineering CPD courses based on both software and design courses for all of our participants. We have several different types of courses ranging from some very popular software such as Procon, ETABS, and so on, as well as other premium design courses such as our high-rise course, which has been very popular, especially since of late. Just to introduce our resource person today, Professor Priyan Mendis is a professor of civil engineering at the University of Melbourne. He received his PhD from Monash University, Australia. He has been an expert consultant for the design of tall buildings in Australia, and as well as several other tall buildings constructed worldwide, including some of the tallest buildings in the world. He's also an active participant in the World Tall Building Council, CTBUH, since the early 1990s. Professor Mendis has also written more than 400 papers with more than 13,000 citations. So without further ado, I'd like to invite Professor Priyan Mendis.
So thank you very much, Ayesha, and also Chatumi, for organizing this session, and is part of the recent launch of the Colombo School of Engineering as well. And we have today the first batch of students also attending this talk. And also thank you very much for joining from here. Particularly on as well as there are there are others joining the webinar as well. So I selected a topic which really a key topic now, where we think the concrete is the problem for all these sustainability issues. I will explain through that. Also, we know that the solution. Concrete is a solution as well. Not only the problem, but it is a solution as well. So we will today discuss. I want to go to the basics first, because to understand the sustainability, to make it concrete sustainable, there are a number of young people in the audience here as well, and here and also joining online. So just want to mention that the basic concrete technology, just to remind you as well, you have done this, you have done this in the undergraduate courses, but the way we are teaching concrete, I think we need to have a bit of a change in how we teach concrete in the future. So I will just start with some basics, the slides, and then we'll get to the So just to talk about the outline of my talk today is that actually Sajivan has sent a message, and I said now it's okay, sure. So please feel free to, if you want to have any burning questions, not talking about fire today, but any questions there, just let me know anytime. You can ask questions, interrupt, and put it to the chat site. Any questions, and even the audience here, and also online audience here can ask questions, interrupt, and ask questions here. But the others online, there are a number of people I see, close to 80 online. So with the we can put it in the chat side. I will try to answer straight away, but just useful to get feedback and answer. I like that interaction, not just one way there. And today the idea is that to spend bit of about let's say 1.5 hours or slightly less than that, and then we can have a bit of discussion on where we are going. So again, I'm repeating here, but a number of what I have done in Melbourne Uni, and also when I give talks recently in Athens University, I gave a talk on concrete. So there are a number of places in Manchester as well recently. So I think my main point is that we need to really know the basics as well as how we teach concrete now, how we learn concrete. I'm someone who learned concrete at that time. I really like concrete. Thank you for the kind introduction, Aisha. But just I can tell my concrete story where starting my projects in concrete, and I like concrete here when I was studying here, as well as my PhD on the concrete side at Monash, and continue my research and develop a very large group. And then I have coordinated some international groups as well in this area. So I can present the latest work, what's happening around the world. But again, I will start with the basics, and I'll tell you why we are not really teaching properly concrete at the moment in a number of places around the world. Because we teach in a different way, prescriptive way. We need to look at the performance more. Performance of the concrete, then only we can make it sustainable. So sustainability is easy if we know the basics in concrete. And so let's start with some basics. That's where this could be, or you could be already knowing these basics, but I just want to remind you. Let's start with the brief history of concrete coming from, as I said, coming from Greece, spending a bit of time recently. It's really been it's a material. It's used by Romans 2000 plus years back, but the roots are there to the pyramids areas, to the time to even in Greece. I was looking at the Olympic Stadium, which was in fact which was done in 700 and I still remember the history, the 726 BC, which is getting into more than, I think, how much when you count, close to 3,000 years. So there was some, when I was looking at the structure there, the first Olympic Stadium, there was some mortar there. You can identify some of the mortar even in the other structures in there. So although we say used by ancient Romans 2000 plus years back, now I'm going to modify some of my slides after that trip. So so knowledge of concrete is lost in Middle Ages. Then we get back to why talk about history. I like to talk about history as well in concrete, just the Portland cement. So why we still call Portland cement hasn't not changed. We still use the word Portland cement because it's really, yeah, it looked like the English Portland limestone. We are coming from so the Portland cement was in fact patented in 1824. Reinforced concrete was developed in 1850, and one of the world's best inventions is the pre-stressed concrete. And I will just mention very briefly about the pre-stressed concrete. Today is not a totally structural design lecture, and more I will focus on the technology, the knowledge which is missing at the moment in the practice. I'm talking about around the world, as well as in the other places. So some examples where I have to thank Dr. Raquel Nicolas, Saint Nicolas, who from France, sometime was one of my research fellows, now a lecturer at Melbourne University. She gave me some of these slides. But so the concrete for bridges, this is something I have also used. One of the best structures, if you have a chance to go and see in Switzerland, in the Alps, the wonders as well. The bridge in the bridge. Sorry, some automatically goes, but I want to spend a bit more time on those slides. So I'll just take over the. Sorry. Let me correct it. Sorry about that. I think should go backwards. Let's go to the top of the presentation. I'm sorry, it moved very quickly. Okay, going back to my slide on the bridges, again, the concrete applications are, there are wider applications. And again, the Melbourne skyline to Sydney, where Melbourne, where I had some experience working in a number of tall buildings there, and some of the Sydney as well, and then other structures as well. But where the tall buildings are at the moment, the Burj Khalifa is a very good example where I will mention my experience there with the Burj Khalifa work, and there are a number of concrete structures where it's been used. My entry to concrete is where the high strength concrete and all that are in the Petronas Tower on the left hand side, still the tallest building in Malaysia, but it's still been overtaken by the Merdeka, the PNB 118, which I had a chance to work on that bit more. This is when I was studying, when I was doing my PhD. Ken Day, I have a lot of respect. I consider him to be the best concrete technologist ever in the world, a practical side. And he was like my mentor. So I had to acknowledge with a lot of thanks to Ken Day, who taught me a lot of concrete technology, practical side of that. And he passed away a few years back. And he got me involved in the foundation. He was advising on the foundation of the Petronas Tower. And don't look at the time it was constructed, then you'll guess my age. So, but that's all right. But so in terms of the foundation, so up to 80 MPa concrete was used, and as a student I got involved in this. But working with Ken Day, and then the next one, which I really had this is where I was a project engineer especially for the core structure of the telecom corporate building, where high strength concrete was used first in Australia, and I think one of the first applications in the world. We are quite proud that I introduced that to this one, and I got the award for the contribution, outstanding contribution, by the Concrete Institute for that work. So that's where my roots began in concrete applications on the field, which I continued in a number of places around the world. And with the Melbourne skyline, I think I already mentioned a number of structures which I got involved. These are some of the other work I got involved. The World Tower, where the core and columns were high strength concrete, to other places. What I want to say in concrete is not just for buildings. There are actually, in fact, we need to think about the infrastructure as well. So in this case, I want to just upfront say this one. Again, the seawall in Sydney Airport, which I got involved. In this one, the concrete strength was not the parameter. It was the durability, which is called we call the RCPT value, rapid chloride penetration test value. Even the practicing engineers to the academics, I think it's good to know some of those techniques. So when you look at the chloride penetration for durability, we look at the RCPT. That's coming into the drawings now. In this one, the criteria was the Coulomb value. RCPT value was 1000 coulombs. Yeah, it's not the concrete strength, but concrete strength also there. But the Coulomb value, which we had to satisfy, it was not easy to get that 1000 coulombs because it's all about durability. So when it comes to the sea walls and all that, it's the durability. We are looking foundations in buildings close to the sea. When we're working on the Lotus Tower, we had those concerns we addressed at that time. Similarly, a number of other structures. Now, the Seoul Tower, which was more of, I recommended high strength concrete at that time because we wanted to reduce the axial shortening. That's elastic modulus of the concrete, and rather than anything else, sorry, not reduce, increase the elastic modulus, so that we know elastic modulus of concrete is directly proportional to the root of concrete strength. So always remember, if you have a problem with reflection and other things, you can think about why not increase the concrete strength to get the elastic modulus. These sort of solutions, as engineers and others involved in the construction industry, we have to think about the solutions there. And this is, in this case, actually this was, I was not involved, but I just put it here. But this low shrinkage was the criterion for this bridge. So we need to think about what are the performance requirements. We are going away from the code-based methods. It's their last concrete code committee where I've been a member forever now. So about 25 to about 30 years, what we wrote the Australian code, the concrete code. And we discussed about even including some performance-based clauses to start with. This could be the first in the world in terms of concrete codes, if we put some clauses. So we are starting to think about it. So performance is the one. So how these structures will perform, all that. So you don't read that in a code. So we need to think about the improving the performance. In this case, a low shrinkage was the criteria. It's not easy to get the low shrinkage. And even I will talk about aggregate properties later on, why you need to know all that. But low shrinkage also very, very important. Then the Burj Khalifa, where I will have some comments on pumping of concrete. As engineers and others, we need to know the problems with pumping and all that. I'll give an example where closer to a bit more Burj Khalifa. So I was also asked to comment on that at that time when Burj Khalifa had an issue of the pumping problem. So I know a bit more than what is available in the web. But so this is the Burj Khalifa. It's a very, again, I will not spend time on that. Just finishing 3-hour session today on tall buildings in another for another group. I will just will not go in detail to the tall building side, but in this one, it's a critical one with the walls and all that. So we can study these things, especially for younger people studying the concepts. And in this one, my work was on I will have some slides on my work for the Burj Khalifa, why that's what's important. And then the different ones with the where again, some of the bridges to high strength concrete, high performance concrete has been used. High performance concrete is every concrete we use these days. We should call it high performance because we are not just using normal concrete for the structural applications, especially. So we will just continue with that. And in this case, the high strength concrete was just used for the durability and the strength requirements, for nothing else. And the one World Trade Center, it's called a slightly different name now, but that's where with the 102 stories, actually there's a spelling mistake there, but it was completed in 2015. In this one, the dual specifications for high strength concrete was used. So it's a modulus elasticity of the requirement was the dual specifications, elastic modulus as well as the compressive strength. That is the trend coming. Usually we have the concrete specifications separate from the concrete drawings or the construction drawings. But in this case, we will have more and more, we will include, we are going to include more and more of the other specifications, like why we had to reduce the, any questions you have on? But please feel free to ask questions as well. I haven't seen anything in this chat side, but now with the elastic modulus or modulus of elasticity, when you increase that, today I'm not going to talk about axial shortening, we can reduce the axial shortening. I want to say, I always say concrete is a living material. Unlike other materials, concrete properties change all the time. And it's unlike, because other materials, steel and all that, doesn't change much. Maybe we can ask Aisha and Tatumi. Someone is asking, Sunand is asking from the external audience whether they can be recorded. It's your call, not my call. But sorry, so just because, yeah, but you can make some notes rather than recording. But thank you for asking. You could have recorded without asking, right? But you did the correct thing. But thank you very much, because there's some sensitive information here. But you can make some notes. So anyway, the one World Trade Center is a very good example, which is really the 540 meters tall, and as I'm repeating here, but to reduce the axial shortening effects. If you have anyone having questions, I'll have enough time for discussion and questions. But the elastic modulus increase to reduce that axial shortening. Going back to the story of concrete as a living material, the creep and shrinkage, I will not have time to talk about. I can talk forever the concrete, but the shrinkage is basically the shrinkage means if you leave a sample and if you leave, especially the first 2 years, it will shrink. And creep is sort of shrinkage, but under an axial load. So creep and shrinkage are very important when it comes to especially the tall buildings, the axial shortening of the tall buildings. And in that case, the increasing the modulus of elasticity helps to reduce those shortening effects. And those who have listened to some of my tall buildings talks or joining some of these sessions, I will have a separate session on that. Now, why it's happening is the moisture movement, especially. So we need to understand now why it's happening, not just saying shrinkage. I asked some of my students in recent lecture, even in Melbourne, but why it's happening? They knew what is shrinkage. So even one student even knew where the clause. He was saying clause something in the code. But then when I asked about why it's happening, couldn't answer that question. So actually it's okay not to answer because we don't teach. I didn't learn when I was doing my undergrad why it was happening. But I knew where it's in the code, how to calculate that idea. The danger at the moment is all coming from some of these calculations from the computer programs. So we don't have an opportunity to learn the basics. So it is really the moisture movement when you think of. So to reduce the shrinkage and creep in concrete, I want not to just use the slides. I just want to talk. I like talking this all. But the creep and shrinkage is happening shrinkage, moisture movement, but having the aggregates, proper aggregates can reduce the shrinkage. So that's, I'm going to come to the basics later on, but aggregates, why the aggregates important, the properties I will go through very quickly, but having good aggregates will reduce the shrinkage. That's one of the main reasons why we are having the aggregates. Right? We all know, I have a slide later, I may have to skip that slide, but the concrete is cement, right? Going back to the basics, cement, sand, and coarse aggregates. Sand is the fine aggregates and coarse aggregates. So going back to the basics, if someone asks me, what is concrete mix, we just go and say 1, 2 to 4, right? So what is 1 is cement, 2 is sand, 4 is coarse aggregate. Right? I asked one of the engineers recently, what is this 1, 2, 4? And he actually, in fact, gave an answer the other way around. So I thought the coarse aggregates are the 2. But so it's the coarse aggregates are the cement is like a glue, right? Coarse aggregates are there. This is why it's even sometimes called the wonder material. The concrete inventions so long back that changed the world, and the most used product in the world after water, concrete. So that's why we had to know concrete. And in this case, the cement like a glue, gluing the aggregates together. So having the aggregates, large aggregates, also helps in reducing the shrinkage. Otherwise, we can get rid of that. I may not have time to talk about. I have a slide, but I'm going everywhere here just so that to make it I want to put some new things as well. We did some work on what's called reactive powder concrete. Again, it's for a very important Australian overseas structure. There was a very important requirement to protect that particular structure, the roof structure, against certain threats. And that work came from me and working with another one of my good friends. I don't remember Mr. Brian Cavill from the VSL, and he made it like a commercial name called Doctor. And we did we just came up with a mix of 200 MPa. Now these days, my students can make 400. One told me he actually it's a mixed group. Both of them, and a male student and female student, they came up with a 600 MPa concrete. So you need to heat the concrete. You need to put pressure. You can't do it with normal methods. So 400 is easy, 600 in the lab. But in practice, how to get that? So here the reactive powder concrete, if you want to learn, Doctor, 200 MPa, 200 MPa concrete, that is, we can get rid of some of the aggregates, large aggregates. When you get rid of the large aggregates, just start thinking. Large aggregates are where the concrete fails in, it's another thing which you need to remember, concrete fails in tension. We go and do some test, compression test of everything. But we do the compression, but we have to realize by applying the compression, we create a tension, complementary tension field. That's where the cracking occurs. We know the cone type of failure in concrete cylinders and also the cubes. We use both methods to get the compressive strength. We are moving towards cylinders a bit more accurate. So the world is moving a bit more towards the cylinders now. Eurocode, as we know, allow both cubes and cylinders. Australia, we have used cylinders forever. But I think the Eurocodes are moving. There was some discussion recently also when I was in Manchester. We were talking about the British codes when it comes will move a bit more towards the cylinders. A bit more, I think France also. So anyway, Europe allows that both. So coming back to that failure is like a cone failure. It's a tension failures. And I had students, done to death analyzing these ones, understanding why it fails. But the tension failure happens, and we need to really think about the weakness is the aggregate paste, the interface. That is where the aggregates are meeting the cement paste. That's where the weaknesses start. High-strength concrete, I'll explain later, is different. But the cement paste for normal concretes, cement paste, that interface, that name is intertransition zone, ITZ. So that is the ITZ is the one where the failure starts. So you can start thinking about. So to improve concrete, today of course, the background is also moving towards low carbon, sustainable, high performance concretes is the future. But so to do that, we need to understand why it's failing. That's what we are working on. and to even in the industry, we can do in the lab, but we can get to the field. So what we did there was took out the large aggregates, so the weaknesses came out. But then you need to worry about shrinkage and other things. So with the fine aggregates, we need to, we can really fine aggregates and cement. We take out that weakness. That's how we could get 200 MPa in the field. This is a commercial concrete. And we did precast in that case. We had to do a bit of heating to get to 200. And so that was quite useful. Today morning was in another group, I mentioned this, but I had a privilege to be involved about a couple of years back during COVID. We did through Zoom. We were like working on a pre-feasibility study for a 2 kilometer tall building. And in that one, I was all the big experts in the world, but I was invited to talk about materials. How can you do 2 kilometers? So they have seen some of my work on 200 MPa concrete, and 200 MPa concrete is the solution to get to 2 kilometers. So we have and also other composites. So I'll leave it for another time to talk about that. Coming back, I'm still in this slide. So let me move to the next slide. These are very quick ones. The was second tallest building, the Shanghai Tower, 632 meters tall. I had a chance to be really involved in some of the pumping, and also to be Mr. Gong, who was my good friend. That's the Shanghai Tower. There, I think I got a picture of him. That's Shanghai Tower. Yeah, that's Mr. Gong, who was a project director from the construction company. They are in Shanghai construction. This is where the top of the concrete. I happened to be there that day. We were looking at the concrete, especially high strength concretes for this, and so it's actually 507 meters. Overall was 632. Anyway, I'll skip these double facades and all that. If you have any questions on Shanghai Tower, I can explain to you. But lived there and Shanghai Financial Center next to that. Other applications where my involvements in the famous, one of the best cricket grounds in the world, the Melbourne Cricket Ground, was working on the southern stand precast as my early stages of my career as an engineer. I worked on the precast of that, the MCG. I was analyzing the roof of this structure, which is really very interesting. And then, so concrete has many other applications. Even to start with some low-level applications like footings, concrete is there everywhere. So you need to know the performance requirement, what you require from the concrete, what do you like concrete to do, the work. If it's a high-rise structure, it's different to like a sort of footing. Then very quickly, you know, all these applications, concrete can use for concrete roads to then fences to many other applications. So we need to think about all the different applications. Dams, again, when I was studying, I had a chance to go and see the Victoria Dam here. It's really one of the best structures I know of. The Arch Dam, and I had a chance to spend about a week with the labs and all that near the dam at that time as a student. But it's the concrete dams are very, very important. I will not go into the detail. You have a chance to go and have a look at this dam. Of course, if you're not seen that. But again, this is where I'm working a bit more now on the modular concretes, modular construction. Again, the concrete can do things that other materials can't do with the thank you. With the modular type of structures prefabricated. Today, I will not have time to touch on that. We'll leave it to another time. Okay, basics. Let's start with some basics. So it's a concrete. Why concrete? Right? Just start thinking. Then we can go back and use it a bit more, like in applications, because we have the raw materials readily available, and it's a low-cost material. Right? It's a fairly low cost. This is quite important. I had to correct it later on, but Concrete does not burn. Concrete burns and falling happens, but usually much better than other materials. So the concrete does not burn. Concrete is very strong in compression, but concrete has no form of its own, right? There's a spelling mistake here. That's all I need to correct. There shouldn't be any apostrophe there. It's concrete has no form of its own, and concrete has no useful tensile strength. So tensile strength is very weak. But now with the newer concretes, we can make use of the tensile strength as well. I'm talking about one example later on of the work we are doing with the closer to here in Colombo, the material. So again, think about what are the main ingredients. It could be boring to really go back. We already know some of that. The cement and water, as I said, sand, fine aggregates, crushed stone, coarse aggregates. We get the concrete. Just to emphasize what I said, the cement paste is like a glue, gluing the aggregates together, and then we have some chemical admixtures we put to really modify the properties. And so with the cement and then what you do, again going back to the basics. Cement and you have the water, and the cement paste. This really remind you, refreshing our memory of the cement. I know we've got a meeting. So the water to cement ratio, so water to cement ratio 35 MPa. If it's 35 MPa, just assume about 20 liters water. So adding water makes it like no strength drops. As we know, adding a bit more water, strength drops. That's why we shouldn't allow that people to add water on site, right? Concrete strength drops. These are basics, but it's good to really revisit some of the basics. The water cement ratio is a key one. And rather than adding, if you want to have the workability of the concrete, you have to use the superplasticizers now. Admixtures to there. Admixtures, these new superplasticizers, which I'll make some comments, will not change the strength there. So coarse aggregates, the fine aggregates are there. We talked about that. Coarse aggregates, usually the fine aggregates are between about up to about 0.1 millimeters. We normally say in Australia 0.075, but 0.5 can be 0.05 can be a fine aggregate as well. About 0.3 to like the 5 millimeters, all that are coarse aggregates. Coarse aggregates go up to, we know, about 19 millimeters, 3/4 inches. So we will do that. We can use that. Raw materials are readily available, and then we get the raw materials. I will talk about a bit more cement production later. Why I'm talking about all this today is because to get sustainable concrete, we have to understand the basics. Now, why concrete is that popular? It can be easily transported, placed, compacted, and finishing as well. So going back to just a bit of like your really some knowledge that you have like from the undergrad days. The cement is about 7 to 14%. It can vary. It's good to know some of these numbers just to even if I forget some of these numbers sometimes, but because I teach, I remember. But aggregates, 60 to about 70% of the volume. Most of the concrete is aggregates, right? So water, we have to understand there's water there. So certain volume, in this case, 14 to 22%. And the chemical admixtures as well. So again, you have to remember now, concrete does not harden by drying out. Again, when I ask someone, say it's concrete, because we think no, the concrete, the water escapes and dries out and you get concrete. It is not. It is the hydration of cement, which just to remind you, the hydration side, I will have some slides. What is this hydration? Then come to the reinforced concrete. Think about the reinforced concrete. Take one example where the slab, and if you apply the load, it stretches, it's in tension, as you know here. You'll see the tension pulling apart the slab. So concrete is very weak in tension. Then we go and concrete has very high compressive strength, but then that very weak in tension. So we need to go and put some steel reinforcement. So steel bars reinforce the concrete. So the best composite material in the world is concrete. Complicated, but so we need to understand, if you improve the tensile strength, we can reduce the cement. So I'm working towards the sustainability. Steel needs lots of energy to produce. Cement is not now they call about green cement, green steel. Green steel, what they do is the process, they use renewable energy or some other waste materials to produce energy and go and say green steel. That is not the green steel. What we'll do is to really improve the properties of steel to really to make it greener, but it's not happening like that. So wrong one, I think I'm pressing, that's what happened. In this case, the steel reinforcement, it can come in, those who are new to some of these materials, they're coming in the reinforcing form or the mesh, a mesh for slabs especially, and walls sometimes, but the reinforcement beams and other elements, reinforcement can be used. And I don't have, today I will not explain reinforcement. Those who know, you will see that there are ribs in the reinforcement to get the bond, to improve the bond between the reinforcement and the concrete. So if you don't have the ribs like this in the reinforcement, you may not get the full bond between the steel and the steel reinforcement and the concrete. I'll leave that to another time. We can have all these complicated structures, lots of steel here, reinforcement. But the problem, you want to make sure when you're on site or when you work, you can have enough concrete in between. What happens is sometimes your reinforcing bars are too close to each other. So because of that, the concrete can't go in. So the rule of thumb that we use normally is that the distance between the reinforcement, centers of reinforcement, should be less than, should be more than the 3 times the diameter. So in this case, the reinforcement, also the aggregates has to pass through between the reinforcement. So you have to make some decisions. There's places where the concrete can't, we put all this reinforcement, but concrete can't get in. So you have the weaknesses there happening all the time. Other thing what we have done in the world, again, is that like today is I may have time to talk about it, but not sure. But we'll see, depends on the time I will spend on these things. But the self-compacting concrete, and we'll learn more. Now, we do what's called on-site. We get the concrete transported. We do what's called a slump test on-site. Slump test is still the best test for the workability. So slump test, what we do, we fill the concrete in a cone. You can just look at the web slump test. You'll get all these videos to you get all the slides, the pictures, images to all that. So in this case, you will have the slump test done. Once you do the slump test, you can determine the workability of the concrete. We call it self-compacting concrete. That means you don't need any vibrations. So that's the trend is there for that. And we do use a lot now. We want to avoid vibrations, everything. Vibrating the concrete to get the proper compaction. Self-compacting means you have the full slump, we call it. We put water and we put other admixtures to make it fully workable, fully flowing concrete. If you pour that, it will fully flow. That's called self-compacting concrete. So self-compacting concrete is very useful for these sort of applications. You don't need to really, this structure we have used the self-compacting where it's found big rough foundations. We don't go and vibrate, very messy. So use what's called self-compacting concrete. You may have to refer to some of that later on. But so again, I skip this one. And the slabs in the reinforced concrete, you have different type of slabs. You need to put the reinforcement in there, and then get the proper properties. Pipes there, pipes are really done, which really very important to know. Pipes are done by rotation methods. pipes are done, and again the concrete applications. Today, again, I will just touch on some of these topics, but again, there are two ways of learning. You have already know some of that, but some of the things that I want you to start thinking about and reading a bit more, the web and other books and all that. So corrosion of reinforced concrete, that is again the normal concrete. We have also understand we have a high pH value. So pH is about 12. So what is doing it is that it will have a passive layer when it's alkyl, have a passive layer around the steel reinforcement. That will prevent the unwanted materials getting into the steel reinforcement quickly. So what happens when you have the corrosion? See, spray the chlorides to sulfates to all that, and then it will really reduce that value of pH. So carbon dioxide, again with the chlorides, it have an acidic environment. Chlorides will make the hypochloric acids, HCls, and then really reduce that pH. So that will damage that layer and then aggravate the corrosion of the reinforcement. So good to know a bit more basics once the corrosion starts, and even the carbon dioxide or other, the pH decreases, and we are also doing work on carbon absorption, but this carbon dioxide may have some problems in increasing the corrosion. So we have the corrosion, and it's again this expands and rust around the reinforcement expands and can dislodge. Corrosion, see the first cracks there, and the more cracks form. I'm sure you'll be asked to really comment on what sort of cracks are there on site, and so on. So you go to understand. If there are any questions, I'm happy to answer them. So see the problems there, especially close to the sea, but other places also can happen. Basics, and very quick basics there, and then we got to some other material. But so we talked about it already. Have cement, have the water, mix the water properly, and get the cement paste. In a what is a Portland cement? Not good to know why this is happening other than saying we have cement. Just go. I have done this as well when I was studying. So I just memorized these things, but I didn't realize, the importance of going a bit more deep and understanding this. Cement, we can go and buy the cement. And sometimes we think, why bother looking at but to improve the properties, cement plus other concretes, you need to really have this to know what it is there. So Portland cement is a combination, especially calcium carbonates, silica, alumina, iron oxide, some of the calcium sulfates, which is called gypsum. So what we do in manufacture of Portland cement, you can even read from the web these days. Some, not all the information, but you can really see what some of the processes. But I just want to have a summary there. The selected raw materials. So mixing the limestone, chalk, clay are crushed, milled, and proportioned. So it's in a kiln. It's really, we're getting to I don't know why I had the conversion, but to centigrades, why I put steel Fahrenheit. 2,600 to 3,000 Fahrenheit. Anyone can quickly convert to, yeah, that's all right. We'll do that later. I think I still remember. Do you remember the conversion? C on 5 equals F minus 32 divided by 9, right? That's something that's correct. Anyway, we can convert easily to the Fahrenheit to, so very large the centigrade values as well. So the clinker, once it's heated in a kiln, you get what's called cement clinker. Cement clinker is cooled and pulverized. There where the gypsum is added. That's called Portland cement. So it's not that difficult to get Portland cement. That is the process. Get the raw materials from the quarry. Go through this process. That's where the kiln is. And get add some gypsum and other small, like other things. smaller quantities, and then you get the cement mix and then transported there. So let's look at the why. One can say here, or actually the why cement is the polluter. You need to understand that why we want to reduce the cement, to reduce the carbon dioxide, to get the sustainable low carbon concrete. That is the basic thing. Reducing some cement and go for other materials, recycle, which I will talk about that, recycle materials, all that. But the basic thing is to reduce the cement quantity. How cement is, anyone can say this, but why cement is the polluter, why we have a huge amount of carbon dioxide issue with the cement. I'll give the answer, but which you can read a bit more. The calcium carbonates are in these kilns to make cement. Calcium carbonate, which is limestone, we get for the cement production as a natural material. Limestone is converted into calcium oxide. So obviously carbon dioxide is escaped from that process. That carbon dioxide going into the atmosphere, that is the pollution. So it's good to know why cement is there, rather than like now, even recently someone talked about spend 45 minutes talk about cement, all that, and someone asked a question, why cement? But no, it's not fault, but we don't really go deeper into that. So we need to understand why. So the carbon dioxide is escaped in that process. So what do we do now to get the we can't stop making cement. We will never do that. So we have to find solutions. We are engineers. We are the ones find solutions. These are some solutions. What we do, we capture the carbon dioxide. We let it, rather than put into the atmosphere, carbon dioxide, right? It's like, it's okay, just to make it, it's just not serious comment, but we put it in the bags and store at home, right? For some carbon dioxide, like, that's all right. But we can't do that, obviously. So what we do is, we tried some what is called sequestration. That is, we tried to put carbon dioxide under rocks and, so far down in the ground to store, all that are there, but they're not efficient, expensive processes, right? All that. We have been working on this for last 20 years, 30 years, what is called carbon sequestration. We tried to put the carbon dioxide, store all that. Rather than that, these are about now, people have been working on these still solutions. It's not really commercially available yet. What we do is that we have store the carbon dioxide in the cement plant, simple as that. Now, those carbon dioxide, so these are storage of carbon dioxide. How to store? So there'll be some additional things that to be done to store the carbon. I will not go through this in detail, but you have to store the carbon dioxide. Adjust the cement making product methods to really store the carbon dioxide. These are some of the technologies. Calcination is one. I will not have time to really, I won't have time today, maybe another time. But I've just written that converting limestone into lime to burn the clinker. We store that carbon dioxide, reuse that for that carbon dioxide. Other one is called oxyfuel technology. You can read about that. These are all trialing out to really arrest that carbon dioxide, reuse the carbon dioxide even. Direct separation, we can separate the carbon dioxide. Once it's separated, we have to make use of it. Now, this is once it's separated the carbon dioxide. So here, this is the work that we have started doing. And there are two things we are doing. I won't have time to talk about too much about this today, but we have to start thinking about what is called the recycled concrete aggregates. Now, what we do is that when you're demolishing, I'm working towards a low carbon concrete. When you demolish, when yesterday we were talking about this, but when you demolish the concrete, we used to just throw them into landfill or to fill something for low grade applications, throw them into some road bases or something like that. But now we can't afford to do that. Every concrete being demolished, we must reuse it. So what we do is we crush them and then reuse as aggregates. But there's a problem there. Now we have to understand why this problem comes up, because again, I have separate lectures on recycled concrete aggregates, but the recycled concrete aggregates have two phases. That is, one is aggregates touching the old cement paste, one interface. Other interface is the new interface with the new cement paste. So there are two interfaces. Because of that, there's a weakness in that inter-transition zone, IT said. I talked about. I started saying IT is the weak zone when it's the failure of the concrete. So what we have is a weaker IT zones and all that. So at the moment, we are allowed only to use about 30% of recycled concrete aggregates in concrete. So what we trying to do is now, still lab scale. I got a PhD student who was from here, but now working on the carbon dioxide absorption. That is, we use carbon dioxide coming from those cement plants. We try to do that to really improve the interface. What happens is that weaker interface, going to a bit more basics, you have this calcium carbonate. Calcium carbonate is formed now. We are using the positive properties of the carbon dioxide. The calcium oxide is already there, calcium hydroxide. I will talk about the equation later on. Calcium hydroxide is already there in the concrete. It reacts with the carbon dioxide and form calcium carbonate. Calcium carbonate is strong. So then we can use the recycled concrete aggregates more than that 30% that we are allowed to use at the moment. So this is other new things. Use that carbon captured is one for the recycled concrete aggregates. Other one we are trying out is the carbon, what's called carbon curing. Same way, even for other the elements, we will send using carbon dioxide, carbon curing chamber, and we can really improve, we think, improving the concrete. So it's early stages of carbon curing. Third one is actually we are using graphene oxide, which I'll come to that later, to improve that process. We think it'll absorb a bit more carbon dioxide if you have the carbon dioxides. Now, see the cement. Cement is it's very small particles. That's human without human hair, but it's very small. So these are the principal cements in Australia we use. In Sri Lanka, it's used in different countries, different names. Here we have we only blended cements and the normal Portland cement, but we have low heat cements to high yield strength cement. Here we can specially order, but in Colombo. But the other places, where I'm used to in Australia is different types of cement, sulfur-resistant cement for the more marine environments offshore. Select the type of cement. But all cements are these days blended cement. Portland cement is mixed with about some 30% fly ash or so. All cements we used in Australia like that. So we are going towards blended more. I'll leave it to another time to talk a bit more. But maybe that's useful information. Up to about, we are allowing about 7.5% of mineral admixtures, till we can call it Portland cement. So we can use about 7.5% of other materials and to use the name Portland cement, but not more than that. Some countries allow more than that, but then we had to go to the what's called blended cement category if we don't after 7.5%. Again, these are some of the basics you can read from the web and all that and other books. But so used in general purpose cement is used. Blended cement is very popular now, high yearly age cement. There are a number of applications when you want to remove the formwork quickly, get the strengths quickly, all that. Other one is a low heat strength cement. That is the, if you want to produce low heat, have the low heat cement. Sulfate resisting cement is where the groundwaters and close to the sea and all that. Cement constituents. I'm not saying that you should remember all that. Go back to basics. Try to remember what is the how cement is made of. Then we can attack that, make the cement much more low carbon, user friendly. C3S, the tricalcium silicate. It's the early stage in the world, these things. We don't try to manipulate these ones yet, trying to make it low carbon. These are things some of us are working on. And I think the dicalcium silicate, tricalcium aluminate, C3A. So these are the main components of the cement. There are a few other smaller level compounds. You can look at that information. So usually I will not go into detail. These are the if it's high early strength, what we can do is we can really reduce the C2S component a little slightly. And again, for low heat, we can reduce the C3S component. So we should know how to attack that, how to make it really happen. And if to make it sulfate resistant, there are again that reduces C3A component a bit like that. And so we could really do things to really manipulate the ingredients. So you will see all that in the future, not yet done properly, but in there. Going back to the basics, again, don't read from this one too much, but just try to remember why we, as I said, cement hardening is not escape of water. It is the chemical reactions. What's happening? What's called the name cement hydration. Right? Cement hydration means hydrating that. So C3S in the cement react with water and get to C3S2 CSH and calcium hydroxide. C2S again with water, then you get CSH and again calcium. Thank you. Calcium hydroxide. Calcium hydroxide is the material which is really generated from that cement hydration reaction. Now, what we do now? Now, again, I will not go into detail today about you have heard about some admixtures, right? Phosphoronic admixtures. We use fly ashes. We use, it's really now become basics. As I said, 30% fly ash is in every cement in Australia. Here we got blended cements. Now, fly ashes has silicon oxide, SiO2. SiO2 will react with the calcium hydroxide and form more CSH. So that is all it's doing. That's why they are called phosphoronic admixtures. They will join the chemical reaction. That's why it's a phosphorons means that. So you have the calcium hydroxide in the basic cement reaction. The ingredient works the reacts with water and form calcium hydroxide, and CSH is the concrete component. And so the calcium hydroxide is converted into more CSH by these silicon oxides in those admixtures. What are the admixtures? Again, I will not go into detail. Fly ashes, slag, silica fumes, all that are waste materials. Waste materials, so they are either made in the one problem is that even here you get the coal fire plant, the thermal plant where to get energy. In Australia, we are really closing down because it's a polluter, right? Carbon dioxide escapes in the thermal power plants, and so it's number of pollutions happening there. So people are getting rid of the cement thermal power plants. Australia is a country where coal is one of the main exports, but still we're not allowed to have any more thermal power plants, and they're going to close earlier than we thought. So what are we going to do to coal? I don't know. It's where economy or something depends on the coal. And here I know we had the Norwich plant here clearly, but it probably still for now it's okay. So fly ash we are running out, but we have a lot of fly ash in. I'll leave it to another time. Talk about fly ash. Maybe I'll just mention the fly ashes from the thermal power plants. What we used to do was because they are small powder as a waste material coming out of that energy process. You can learn about that if you want to a bit more. We had to use to the ponds water. When you put the water, then it won't escape. You can't just dump them and put it outside. Then they will go to the atmosphere and pollute the atmosphere, even the small fly ash particles. So what people used to do was to put it in the ponds, water. So we have what's called pond ash. Now we may have to extract them once the thermal power plants close. So it's a very expensive process. So we even had work done on pond ash, but cement manufacturers are reluctant to really use the use that pond ash. But fly ash is a main ingredient which still we uses. What cement manufacturers are doing, you will read this in the web. What they are doing is to really reduce the cement clinker component is to really add a bit more limestone. So limestone cement will become a bit more popular. When here you get limestone cement. Limestone cement, there's a limit that you can use the limestone to mix with the raw cement powder, but it can be used. So limestone is used a bit now to really reduce that clinker content and to make it a bit more carbon friendly. And you can read about a bit more about limestone cement. So getting back to that, this waste material is coming out of that coal fire plants and the other materials. That the slag is a material which is really very important material, and the silica fumes and all that, but coming from the iron furnaces as waste materials. So these waste materials as yes. Yeah, this is the phosphoric reaction we talked about. That calcium hydroxide reacts with the SiO2. Yeah, that phosphoric reaction means, actually for the audience in the webinar, I want to say the question is adding silica fume, how it's become, why it's a phosphoric reaction. Now, phosphoric reaction means that reaction I'm talking about. That is that calcium hydroxide, right? Calcium hydroxide reacts with the calcium hydroxides react with this CH, right? That's calcium hydroxide. Reacts with the SiO2 in the silica film and make bit more CSH. That is why it's called a phosphoric. That is the phosphoric reaction. That's a very good question to the audience in the webinar. I want to say that the question is good question. That is the silica film has two effects. You are really right. What is the phosphoric effect here? That is the reaction of CaOH2 plus SiO2 make bit more CSH. That's phosphoric part. And you are really correct. Particles are very small, smaller than cement. It has a bit of filler effect as well. I got a slide later on, but it's a good point. So it has both effects, will make it a bit more compact concrete. But the strength increase of silica fume comes from this reaction, a bit more. Of course, the filler effect will have a bit more compact as well, but mainly coming from that phosphoric reaction. Very good questions. There are other reactions happens in chemical reactions in the hydration reaction. C3A also form what's called ettringite, which is it's not really good for the durability of the concrete. Again, I will not talk about it. If you're interested, read what is called delayed ettringite, DEF, delayed ettringite formation. Ettringite within can form later on and expand the concrete and may have some issues of the break in the concrete. So that problem sometimes arises after so many years. So DEF is the word. I will not spend time today, but this ettringite formation is again, it doesn't help the concretes. So that comes from the C3A. So you can reduce some of your C3A. And then if you want to make it a bit more durable, and if you think there's the ettringite issue. So like that, you can know the basics and just attack them to really to make it for the adjust the cement properties. So again, I'll skip that one, but the reactions could happen. Only thing I want to say is the cement reaction, right? Cement reaction can happen. Hydration reaction happens with time. We sometimes forget that curing means you provide enough water for the cement hydration to continue. We don't realize it can happen up to 1 year, up to even later on. So that's why we had to, initial curing is quite important, of putting water and other methods of curing for the hydration reaction to happen. So think about that curing is a key to get the good concrete. So again, I will not go into this, but properties of Portland cement, that we need to be worrying about setting time. We want to select the Portland cement, the cement strength development, volume change. I will not really go into this, but more of the concrete side, the durability. So let's look at this one. Also understand the heat generated on the y-axis and the time on the x-axis. Heat of hydration is the key. Now, again, I will not have time today to talk about what's happening. We have to, in specifications, we need to limit that heat generated to about 70 degrees. There are two things we do. The heat generated when concrete is mixed, we keep it that heat, the increase temperature due to that the hydration reaction about 70 degrees. Other thing we do, try to make the difference between the middle of the concrete and the outside surface to less than 20 degrees. We do that. And so those two things good to satisfy. Different places they try to do that, but this is what I'm following forever. And I had even PhD students working on this area. But so that is there because to reduce the cracking. Because excess heat will generate some smaller cracks within the concrete. So those, to avoid that, we have we put like now to reduce to 70 degrees. Now what do we do, right? To really actually, if you like, you can even sit here. No, you like to sit there. So if you can't see, just come here. It's all right, because all of you are covered as well. So good to see that. Because I'm not using the lectern. I'm just more comfortable sitting down and talking. So feel free to join us here. It's all right. But I know the webinar audience, I'm sure you can see the slides as well. Now, with the 70-degree thing, it's quite important to understand. We have been working on wind turbine foundations. We have been working on mass concrete. We talked about so reducing heat of hydration is the key. And now we can talk about low carbon concrete, all that, but we have to make sure these things, basics are satisfied. That's one of the main messages I want to pass today. But so heat of hydration, 70 degrees, what do you do? So you can use fly ash or slag, which will reduce the heat of hydration. So they will increase the workability as well as reduce the heat of hydration. We talked about silica fume. Silica fume increases the heat of hydration because silica fume reaction is very quick, and fly ash and slag slow down the reaction. So reduce the heat of hydration. So we need to, as engineers these days, not only just the concrete technologies, we need to understand these things to really look at. We had to approve the specifications. Right? We are the ones who had to sign off specifications. There are legal cases I can't name, which I had to help some of the people who are in trouble in courts. We go as like giving expert witness, expert advice, sorry, not advice of things in the courts. Mostly it's settled out of court, but we have to give our opinions as well. So these are legal implications of this. So by having fly ash and a little bit of slag countries, special fly ash, we reduce the strength generation in the concrete. So early age strength, I got couple of slides on early age strength. I think I'll get to that, but early age strength. but you can reduce the earlier strength by you will have a reduction under the fly ash and slag. One of my experiences very quickly is that these are things you will not read from the web, but the books, but the post tension, the people are doing all the post tension, especially the dead end type of anchors. By putting fly ash, it didn't generate the early edge strength, and then have some explosive failures in some cases. Luckily, occupants were not there. So having those admixtures, we can make it low carbon, we can do all that. But we need to look at the basics and say, what is the performance requirement as well? There's a danger in the world. We go and reduce everything. We use some of the materials and try to say, right, this is a carbon reduction. Marketing people will say, I want to market this. My cement is the best cement in the world, low carbon. But we don't know what is the performance. We need to, that is what is missing. So in the world now, and the marketing people sometimes take over, it'll get corrected because there could be some failures. Failures have happened in the past. So we need to be careful. I won't have time to talk about failures today. But again, heat of hydration is one of the very important ones. We can do the modeling. The recent work, even CSEC, doing that wind turbine foundation work, monitoring the temperature, modeling there are modeling methods, and also to really, some of them, the people who work on this, I think would be joining the webinar as well. But that work, the modeling and all that, we have those capabilities now. But you can monitor and say, well, it's more than 70 degrees. Victoria Dam, all that ice had to be used. Ice had to be mixed, or the nitrous oxide, which really called artificial ice, to reduce the heat of hydration. So mass concrete, especially thick elements, you have to do that. But what's happening with the high strength concretes and other type of concretes now, you may have, you mentioned silica fume. It's really silica fume. If you know how to do that, it's okay. Otherwise, we need to be careful about the, even for thinner elements with the heat of hydration. So all these things we need to think about. So if you want to adjust I mentioned we can adjust the constituents, components, play with the C3 and C3S. You can really, so it depends on the C3A component and C3S component. I showed you a table before how you reduce, like you adjust the C3 and C3S. So yeah, these are more for cement manufacturers, but we have to give the input sometimes. Effect of admixtures, I mentioned about the, you can heat it, you can sometimes use some chemical, we call it retarders, some chemical admixtures to really reduce that heat of hydration. Delay the reaction. So fly ash and slags and all that automatically reduce the reaction. So that's the heat on the y-axis, time on the x-axis. So just there are some chemical admixtures can be used to retard that. Set-in time is a key one. I will not spend too much time on set-in time, especially with the different climates, the set-in time, I'll skip that. And very much with this graph, yeah, we can start thinking about these things a bit more now, because we don't sometimes think, yeah, we get the concrete, we only look at the performance. But in this case, the C2S components, how it can really lead to that initial set and the final set and the hardened paste, like, the glue around the aggregates to C2S to all that. Now, C3A, I mentioned, will have some guide and all that. So there are some problems as well. I'll leave it there. But then just a very brief one, why we measure in 28 days, strength on the y-axis, time on the x-axis, 28 days. See, most of the strength is developed in the first 28 days. That's why we have the characteristic strength measured at 28 days. It's not a magic number, it's just happened to be there. But with the newer concretes, we still use 28 days. But now, more and more, we are using some 56 days strengths. And we can use 1 year strength. If you're designing a structure where only occupants come after 1 year, all that, you can smartly use the elastic modulus, the strength increases by about 15%. I normally use about 15% increase. Now I'm getting towards this low carbon concrete, where we need to be smarter now, using these newer things, not just throwing some materials and making it low carbon, but try to optimize the structure as well. So optimizing the structure, use some high strength, high performance concrete, as well as use some smarter techniques, because we have to understand it'll be occupied only after, let's say, 1 year or whatever. Use a bit of higher strength, but you need to get the approval from the clients and the certifiers. But you can, so that's why you have some enough knowledge for that. You can easily use 56 days now. I just tell people use 56 days, because you will have some strength increase, right? And rather than putting in the drawings 28 days. So for that you need to, they're not the people, they're not doing that. We are the ones who know the performance required by the concrete structure. So then we are the ones who know only 56 days, all right. Tall buildings, or even other ones, I recommend use about 15% extra, and so on. So we can use that. So that's where the curing is quite important. Strength on the y-axis, time on the x-axis. If you cure if you put moist cured, put enough water all the time, you can get the first top one, have the highest strength development. All depends on how you cure the concrete. And curing concrete, I can talk for hours, but what is basic is put some enough water to hydration reactor to continue. So different methods. Try to erase the escape of water. You can even use curing compounds so that you trap the water inside and provide enough water within the concrete for the reaction to continue. That's what we are doing. Sometimes we put some polythene bags on top, right? To really prevent the water escaping. Sometimes we put some water ponding. We put some pond of water for that. So curing is quite important. Just remember that by doing these things, we can get the good concrete. So that's to get the low carbons as well. So the volume change can happen with the cement. I'll skip that. Permeability is quite important to get the durable concrete. I will not have time too much today to talk about it. The permeabilities in the concrete, once you mentioned about filler effects, all that will reduce the permeability of the concrete. That means compact concrete is more durable, so that unwanted materials, chlorides, the carbon dioxide, that all that unwanted materials will take more time to attack the reinforcement by making it compact, durable concrete. So low permeable concrete is a key. I'm really aggregates. I may have to skip about the aggregates without saying too much. Good aggregates are essential, but I'll skip that, but I want to just mention this. The aggregate size distribution is a key. Again, the filler effect type of thing. You have to have a grading of the aggregates. The term grading of aggregates is a key to obtain the so the grading is the key. Different type of aggregate sizes. Okay, I think I'm going back to a good question in the chat side. In pile cap in concrete, what are best methodology to mitigate the heat issues? I think it's really, even for pile caps, the similar methods can be used. Try and use a bit more fly ash, as long as you get the strength requirements properly. Slag is another material. We are even using some, these days, what's called triple blends. Silica fume, slag, and the fly ashes. What's happening in the world, we'll have some issues. It's already happening. Fly ashes costs are going up. People want to make low carbon concrete, reduce the cement, try to throw in a bit more fly ash, slag. We can use slag up to 65% we are using now. But we are going to run out of slag, and slags are getting to be expensive. That's why we have to have some new material. So the answer to this question on pile caps, similar methods can be used to really reduce the cement content a bit more, use some fly ashes. And my early stage of fly ash, even I have done this as well, some others, but every concrete underground, we recommended fly ash to be used, because fly ash not only a waste material, it improves the durability of the concrete. Slab similar. So especially for pile caps, so you don't need sophisticated the water lines and all that for pile caps. Rafts, sometimes raft foundations in cover rafts in the world in some tall buildings, they had to use some either the pipelines to cool the concrete, internal pipelines, or else, as I said, the ice, nitrous oxide, artificial ice, to really reduce the heat development in the concrete. So pile caps, you don't need all that, but I think the best method is just use some bit more fly ash and slag. That will reduce the heat of hydration. I hope I answered that question. Right. Fly ash is especially the acid attacks to chemical attacks, really. As groundwater has all these components, so especially that. So aggregate size distribution, I will not go into this, but you are used to this type of graphs where grading graphs. And again, I don't want to teach you about the grading graphs, mixed designs another time if you have questions. But depends on we do what's called sieve analysis and then get different size of aggregates. That gives that compactness, durable concrete. We have many issues now at the moment, honeycombing to problems with concrete, all sorts of things, because we don't get the aggregate grading properly. And so we need to really make sure it's really satisfy the grading. Actually, we don't even know sometimes they don't even supply us the grading of the aggregates. They just said aggregates have been used. But it's good to really get when you from the concrete suppliers, what is your grading? It's quite good to have that. Aggregate grading. Durability of aggregates are quite important. The abrasion means the breaking is had to be very strong. Chemically without any actions at the aggregates. I will not have time to talk about everything today, but we are using glass. Try to use waste glass now. Waste glass has more silicon oxides, SiO2 again. That silicon, the aggregates have some bit more reactive aggregates, which are called some alkalis, unwanted alkalis. They will react with the silica coming, even without glass, have some more silica in as a material. So the silicas, that silica reacts with the alkalis and have what's called a major problem called alkali-silica reaction, especially bridges and all that. ASR, the word ASR, look for that term. And there are problems with ASR. Now, our problem is when you use the glass as a replacement of aggregates to make it a bit more, to make it carbon friendly. What we do then, what happens is that ASR you need to prevent. We have some solutions. We had to thank Professor Mike Thomas, who well known to me, who came up with he found that fly ash, up to about 30–40% of fly ash will reduce the alkali-silica reaction and slag a bit as well. Continuing from your question on what is durability on fly ash, ASR is another one. So what we say is, we have done this work. We put the waste glass, replacing the normal aggregates. It's reactive, of course, because of SiO2. We throw in about 40% fly ash, it goes away. ASR. So we have solutions. So we can't ask the concrete technologists to provide these solutions, or the cement manufacturers, concrete manufacturers. We have to give those solutions. Production of high-strength concrete aggregates are there. I'll go through very quickly the next 20 minutes. But so production of high-strength concrete, the selecting suitable aggregates, type of aggregates. We found that this is work PhD from Dr. Kasun Chanaka, still senior, research fellow, still works with me, but have done some very good work. his PhD from here. He's working in CSEC as well with those days. But he also did this work with Holcim, Australia. We found the different type of aggregates. High strength concrete is because we are making, what we are doing in high strength concrete is we are making the paste very strong. Making the paste very strong and with mentioned fly ash, silica fumes to other materials to make the paste better and other admixtures to make the paste better. Then it's not the weakness, is not the aggregate glue cement interface. I mentioned IT said before, the failure starts there. High strength concrete, it breaks through the aggregates. So because of that, we need to do other things. Right? Again, I don't have time, but when you're doing the shear designs, we rely on what's called aggregate interlock, right? Interlocking of the aggregates. So aggregate interlock actions are reduced in high strength concrete because it breaks through the aggregates. And so good to know why these things are happening. So what we do in codes now, I was heading the Australian Concrete Code Committee, which was taking Australian code from 50 to 100 MPa. And so what we did was we put a ceiling, a maximum limit on the strength of concrete that can be used for calculations. We can use 100 MPa, 120 MPa concrete, but for shear calculations, we can use only 70 MPa as a concrete strength, just for shear, because of that aggregate interlock actions. So these sort of basics are quite important to know. So anyway, high strength concrete, to produce that, you have to have the good aggregates. No point just doing everything. Seen people working on the paste, trying to put nanomaterials to many other things, but then have some of these weak aggregates, you won't get the high strength. Of course, as I said, reactive powder concrete, at that earlier I said, you take out the coarse aggregates, and then of course you take out the weaknesses, but becomes very expensive. Concrete is cheaper because of the aggregates, coarse aggregates. So we can't just take it out unless we have special applications. So that point is very important. Other thing happening in the world is that this graph, I like this graph. I didn't do this graph. In fact, I know the person who did this in one of his papers. The specific surface area on the y-axis, particle size on the x-axis. This explains everything happening in the concrete up to now. See what happens initially. Going back to a bit more scientific basics. So if you ask the concrete manufacturer, he or she will say, right now we start from this, that, but this is the research. This is where we were before. We had large particle sizes. Our specific areas were lower. Then we went on and then used some of the smaller materials. You mentioned silica fume is a smaller material. Fly ashes are slightly higher surface area than could be cement, but they all can add to that. In this case, fly ash is mentioned to be slightly lower. You can grind the fly ash. You can have ground fly ash, grind a bit more if you want. And then you have this clay. I won't have time to talk about clay. Will become very important. It's a waste material. How much clay we have here? We have in Australia. We are again that Dr. Raquel Nicholas doing some work on the Australian clays, trying to replace the fly ash from the clay. I will not go into that too much today. The word is calcined clay. If you want to make some note and have a look at it later, we are replacing fly ash from calcined clay. Calcined clay means burn the clay. What do you do with the bricks? Right? We burn the bricks, burn the clay to get bricks and make it stronger. Similar thing. So if you have the clay, that's the kind of new work we can do. So trying to use some of these materials. Those days when you try to use clay, not interested. But now all the cement manufacturers have got really interested on the calcined clay because we are running out of fly ash. So fly ash can be a good replacement. Fly ash is calcined clay. Silica fumes, you mentioned very high surface area. So better. Now, this is where the high strength, high performance concrete came. We use some of the newer materials, admixtures, phosphonic admixtures, all that. Made high strength, high performance concrete. We talked about before. Next phase is to make it nano-engineered concrete. Bit more nano materials. I started using nanosilica, but it didn't give me all the. I had a PhD student originated from here, Dr. Madhuvanta Rupa Singh, but she did that work. Her PhD was on nanosilica in concrete, and we went to nano materials, but everyone went to what is called these carbon nanotubes. Carbon nanotubes are very strong, right? Very strong materials, but they are not really, it's very not easy to manufacture, right? They are expensive. They will never come to concrete, carbon nanotubes. What we are working on now is that, again, I will not have time to talk about in detail, but we are working on graphene. Graphene is Sri Lanka is the only country having vein graphite. Vein graphite means purest type of carbon. So there's a graphene plant done by LOIC, the CGT group, in Homagama, which is really, they are converting the graphite into graphene. Graphene oxides, I got 3 PhD students working on this now. Graphene oxide, when graphene came and when they had the Nobel Prize in 2010 in Manchester, that's where I went recently. They have a big graphene center. This Nobel Prize winners were not there. No, not there now, they are in different places. But they came up with the graphene, came as a wonder material, everything, but then it becomes too expensive, bulk production. That's why we couldn't use in concretes and all that. So now graphene oxide, this company manufactures for a cheaper way. That's why we think we can, actually we put graphene into this building as well in columns at the top floor. And some of the graphene went to this floor as well. So in that case, the GO is water soluble. That's why we can use it with concrete very easily. It gives very high strength properties, at least 30% increase in compressive strength, tensile strength increase, all that. Graphene is a single sheet of carbon. So when you have single molecule sheet of carbon, and you can read about graphene, so that to get the graphene is very strong. When you go into different layers, that adds weaknesses, right? Material becomes weaker. In this case, single sheet, right? 1D material, 2D material. That's why it's very strong. So the graphene, to get graphene, how they won the Nobel Prize is that they took a pencil initially, right? Took a pencil, and if you take even a normal pencil, you can make graphene now. I can make graphene now, but not the best form. Take a pencil, graphite, no, normally pencils are graphite, and you can draw on a piece of paper until you get thin and thin layers, right? If you get very thin layers, you get that single 2D material. So even we can make graphene, but not that easy now. But there are other processes of making graphene. If you like, you can follow what's happening with the CGT here. And I think there's another question which I'd like to answer. Rather than using the waste glass in the concrete, recycling them might be more sustainable. No, the reason is that recycling glass, now there's a question asked on why can't we recycle and make bottles? There are 2 or 3 reasons. Why we have dirty glass. For concrete, we use process to clean a bit and use them in concrete, because making glass again is expensive as well as energy intensive. Yes, you can use that for some glass, but for most of the glass is contaminated, waste glass. So also there's another problem with glass is that the glass has glass is colored glass and normal glass get mixed, right? So that then very hard, you can't make glass again. That's the problem of recycling and making glass again. Other issue is very expensive to clean it as well. So there are some contaminants. Concrete can absorb up to a certain extent some of you don't need to be pure for concrete. That's why concrete is very good material. But don't think concrete is like a dumping ground, right? You have to be careful as well. But concrete can absorb up to a certain extent some of these contaminants and materials. So the answer to that is it is really the waste glass. Yes, it can be expensive, but can be recycled to making bottles and all that. People are doing it, but mostly waste glass coming out of we use that. It takes very expensive to clean it and make it pure to make glass. So concrete is a very good application of waste glass. I hope I answered that question. Now the other question is in the chat is if 3D materials, Mr. Brennan is asking, if 1D materials are used, how can we ensure the flakiness of the particle? So I think it's a good question. So what is happening? Good question. Once you make graphene oxide is water soluble. That is why we can use in concrete. Water solubility means, so it adds to the production process, make it easy. We can't just use pure graphene in concrete, no point, powder. So that is the big strength we have. Yes, we have used silica fumes, we have used fly ash. They are not water soluble. So we call it hydrophilic, the graphene oxide, one scientific term. Graphene, because it's water soluble, it can be used like admixture very easily in the process. So we can avoid, but however, it has to be properly mixed and all that. So I'm happy to communicate and answer a bit more later on. And there. What is that? Yeah. So anyway, thank you. That gives an answer. Yeah. So there's another from the structural SDI team. Some of the in the chat as well. Have a look at that. And so going back to this point, where we are heading now, nano engineered concrete. Graphene is a good example. That's where we are nano engineered concrete, nano material, water soluble. That's why I said nanotubes are never good. I said this 15 years back. I had a student doing 6 months of a PhD, and I converted her to just do other things, but because I thought nanotubes are not going to be really popular in the future. But then we didn't work on, we did graphene, but graphene was too expensive at that time. And then now it becomes cheaper, especially with this company CGT in doing that, the production. Let's move a bit more quicker. And I think I skipped the early age. I talked about the temperature development. I talked about the methods where to reduce the heat of hydration. The pumping, I mentioned pumping. Couple of slides to show there's a problem happening where I got a little bit involved in that advisory team. That I'll just skip these ones, but this is where the Burj Khalifa. So where the concrete delivered huge pipes. It's not, we know the concrete pumping around for normal size, but this is a tall building, had to be pumped 500 odd meters on top. So there were a number of issues of pumping. So this is the solution. So these are the pumps. This is the solution. Halfway, they found that the pressure, they can't pump the concrete to the top with that pressures developing. So solution, easy. Reduce that, not only me, I think a number of people agree to this solution, but just a 20 millimeters, reduce it to 14 millimeters. That's all the problem. By reducing to 14 millimeters, a pumping problem was resolved. So if you have any pumping issues on site, try to get them to use a little bit more smaller size aggregates. So these sort of extra knowledge generated could be useful. So from the Shanghai Tower, from the beginning, we learned from Burj Khalifa, some of the lower size aggregates were used. You may have to go down to 10 millimeters. Right? Now, about the low carbon concrete, because we talked about glass in concrete a bit. When you use glass in concrete, we have used for the first in the world to use glass in concrete in an infrastructure project in Melbourne, the Metro Tunnel, one of the largest projects in Australia. Our group, I have to thank Dr. Masood Sopi, who was from one of my former students, was leading that work. That is to put the glass into that project. And the problem working with Holcim there was the glass was hitting the pumps. So these things you will never read in the web. But then we found solutions, we adjusted the glass shape to the We have a process called vortex process. There'll be some papers from our work will appear, which I'm happy to send it later on from that process. Vortex is like aircraft engine. We put the waste glass, and there was a question in the chat also about why the waste glass. Now, we put the dirty glass, and that type of vortex process even clean it as well. So then it reduces the particle size to, we can even get up to about 50 microns. Normal fine aggregates are around 75 microns. So we can reduce that up to about even 50 microns, but that's all sometimes have issues when it becomes smaller also, too small also. Other new work we are doing, some innovative things, is that I don't think anyone has published anything in this area. We are dividing the waste glass particles to even more. We call double vortex process, reduce it about 15-20 microns size. Then we think it will give some, we have got some cementitious properties. Because end of the day, there are SiO2s and all that are part of all that process. So it will have some phosphonic properties we talked about before. So like silica fumes, and we talked about SiO2s. So then this has a glass can have SiO2. At the moment, I will not go into deep of the chemistry, but the problem is what we get in the format is like crystalline glass, crystallinity form. So that crystalline form is not that reactive, but when you break into very small particles, that crystalline form we think will go away a bit. So actually, we got a student working on. So this Burj Khalifa, skip the Burj Khalifa. That's all I want to say there. But quick comments on the linear versus circular economy. We're running out of time, maybe just maximum 10 minutes I'll take. But we can't just take the resources, produce, consume, dispose before we were disposing the material. Now we produce, consume, manage the waste, secondary raw materials are there, and then we have to reuse. We are running out of the raw materials, right? So we have to reuse that. We can't just afford to. This is what we were doing before, linear methods, economy. Just we dispose the waste materials, and now we have to reuse them. It's a good point mentioned in the chat side. That is, even the waste glass, even you can convert into glass again. Plastics we are converting into plastics, plastic oil to do the plastics again. But these are not only energy intensive, but there are other issues are expensive as well. So, but dumping to concrete is a good solution as well. I shouldn't use the word dumping, that's all. But so keep some of that slides. But we will have some new materials, net zero cements. We'll writing some articles. We will see some of these methods. We are trying to use what is called a material called olivine, that is coming from igneous rocks, natural. Using olivine, we think we can make net zero cement, carbon dioxide absorbed in cement. So you'll see a bit more of that in the future. And some of these newer materials we have to start thinking. If we had mentioned to the cement manufacturers and all that, net zero cement, they say, who cares? We don't have time, we don't have. When I was trying to introduce recycled concrete aggregates in Australia, I had a student, Dr. Moiri. He was leading some in Holcim here as well. She was originally chemical engineering, then she did accounting as well, chartered accountant, but she did a study on the economics to technical to all that. She found that we did the work on recycled concrete aggregates. When we talked to the concrete manufacturers 10 years back, they said we can't afford to have extra bin for the recycled concrete aggregates. Now when we go and talk, they say we can have 2 bins if you want to. So this is how the world has changed.
But I could search the web for it.
Downside of AI. Sorry. Normally, no, because I had an alarm for my timing. So that's all right. This is dangerous. That's all. The downside of smart ChatGPT is going to be worse. It will talk to us, even more things will start to tell us, right? What to do, how to behave, and how to. But anyway, I better switch off the Siri here. But so coming back to this, the low carbon concretes, you will see a bit more Number one, Bly Street, you can read the 6-star ratings. 20% of the all aggregates are recycled. 40% of the cement is replaced by admixtures. We talk about fly ashes, slags, and so on. Green ratings are coming. I'm still proud to start the Green Building Council of Sri Lanka in 2009, which I started. Mr. Shumalas helped me at that time. The green ratings are there. We have the system here been developed by the council. So these ratings are quite important. And in this case, Sydney, we have what's called Green Star ratings in Australia. 90% steel has a recycled content, recycled steel content greater than 50%. So the steel being reused, that component. The concrete also had an advantage, what's called a thermal mass. The temperature on the y-axis and the temperature. Concrete has a stabilizing effect of the temperature differences, especially for cold countries. If you go to Middle East, night is very cold, during the day very hot, and similar in some other countries. Now that you can reduce the temperature reduction by using that thermal mass of the concrete. That's something maybe you can, on your work, you can incorporate. I talked about the metacolism clays. Last few slides, applications of recycled materials. And so there are drivers, the policies are changing, that now the governments are putting all these policies. Australia has we had reduced the carbon emissions by 43% by 2030, net zero by 2050. Only 2 countries don't have much of policy, America and China. I think China, of course, encourage that, but they don't have the targets. But targets are quite important. So I'm sure they will follow the other countries. Europe is where I'm coming from. Just another thing, I'm just proud that I was asked to talk about sustainability in Europe this time, the keynote. And they do a lot, but they want to learn from other countries as well. The end of life considerations, we need to talk about the end of life. We need to think about these materials. We can use waste materials in concrete. We need to think about what is happening at the end of the life. And we talk about carbon credits. And if you're interested in the carbon will become a business in the future. Carbon has a value, having a value. So today I will not have time to talk about that too much when I come in December. Also in other seminars, other YouTube talks you will see of mine. I talk about Australia, the carbon credit units. But barriers, we can't procure the materials. We were talking about really cleaning the materials. There's a processing cost. We don't know the properties yet of everything. We don't know the durability. We have the evidence base had to be generated. All of us had to support. I don't think the construction, just the contractors can do that. We need to support that. Standards and specifications had to do that. I'm leading a team in Australia, the Standards Concrete Code Committee, introducing some of these waste materials. What are the implications for the code? I think that's one of the first in the world to have those committees like that. Getting a bit closer to the CSEC building here, which we are here, where you are here now, those who are here, physically present. This is what we did at that time when this slab here. It's very safe, right? But we put all I call it a fruit salad slab. All sort of waste materials we put for this slab, right? So in that area, we put plastics, rubber. I don't think anyone has done this, but the crushed glass, the bottom mesh, recycled concrete aggregates, the textiles. Even we had just to throw in some here as well. So graphene oxide we put, because the waste materials reduce the concrete strength a bit sometimes. So we put graphene oxide to bump up the strength a bit more towards the normal range. And the cube test we did for this slab of it's very good. And so it's very safe, this slab. So it's one of the first in the world we have in this building. Then we put graphene to the column at the top floor of this building. I will skip the graphene slide I already mentioned. Read about the graphene as well. There are some good properties coming up there. And the recycled materials. Think about the construction waste. Trying to, rather than just put it to somewhere, dump it, think about reusing the materials. Right? We even These days, we don't even want to throw anything, right? Just other days when I was growing up, no, if you have some problem with the table, we just say, put it outside. Let someone just go and dump it, But now what we do is we use the materials, trying to use the materials for our advantage. Think about all the materials, all the asphalts on the roads can be recycled now, been recycled. We talked about the other materials. Aggregates, we already talked about recycled concrete aggregates. And we are using glass, we're trying to use paper, we try to use textiles, tires are another application. These are some positive properties to make it low carbon, right? And glass we talked about. Paper also we can use, not easy to use paper. First project we had, I don't think anyone has published this work. So one of the first in the world, we use the paper. If you have any questions, happy to answer. Textiles, we can use put the textiles. Textile will, as fibers, improve the tensile strength of the concrete. However, having textiles absorbs water, so you need to adjust the water content. Paper and textiles both, you need to adjust the water content. You have to have because there's water absorption from these materials. So because of that, you need to do your mixed designs, your income. So this is the kind of knowledge we will generate in the future. Early stages still. Rubber will improve the deformation capacity of the concrete. Rubber is flexible, right? Tensile strength as well can be increased. We are using solar panels. We have a project on solar panels. In the solar panels, we have the glass coming out of solar panels. Solar panels is a big problem, right? Solar panels, we are using all these solar panels. What do we do after end of life? Very expensive to convert. Getting back to this question in the chat side, can we convert into some original materials? To make solar panels, they have to be very clean. To make these old solar panels to convert into new solar panels, too expensive. People are given up. And there are, of course, in the lab we can do it, but to do it in commercial. So what we do, take the solar glass, put that solar glass into concrete. I'm the one who gave the name to the industry person. We got one of the plants coming up. Again, one of the first in the world. In Melbourne, we come up with the solar glass to convert into the process of solar panels. Because glass is the main component of solar panels, right? So why not use in concrete? So, and there are other issues like ASR, we talked about how to use fly ashes. So we are finishing off solarcrete. Other one, I think I'll just keep all this. So the last one is the agriculture sector as well. For low carbon concretes, we're using some of the agriculture, carbon absorbing naturally the carbon absorption of the plants absorb carbon naturally. So this is the hemp. Now there's an article we wrote, Asif and Chatsika was here, but wrote that article on the Daily News, somewhere it appeared recently, on hemp, to show that the industrial hemp is not that marijuana people talk about, right? You know, marijuana is not allowed to be used. Industrial hemp is totally different. So we are using, I'm working with the farmers, trying to use the hemp. The hemp absorb the carbon dioxide, as well as hemp can be used for the what is called hempcrete in concretes and other materials. Hemp fibers can be used. So some of the newer things will have the natural materials, biomaterials, all that in concrete as well. So on that note, so just to summarize what I was talking about, you need to know that's why I was touching on the basics. You need to understand the basics first to work on the low carbon concretes, right? You have to understand why, going back to the basics of cement production, how this carbon dioxide produced. So we need to attack in all those fronts. I told you about the carbon, capture the carbon can be used for the recycled concrete aggregates to strengthen it, or the carbon curings so those solutions can be found. And the other one we talked about is the waste materials. When you use the waste material, especially, you need to understand the concrete basic properties of the concrete properties. You can't just go and tell someone, why not just go and, I have some glass in my house, I'll break it and give it to you. Can you use it in concrete? It can't be done like that, right? It needs to be really properly processed properly. That understanding, we are the only ones who can give that understanding to the industry. So I can remember doing one of the talks here a few years back on the using of recycled materials in the concretes and so on. But again, Holcim organized this talk, INSEE, not Holcim now, INSEE Cement organized that talk. But the now last few years things have really changed in quickly, but we can't really, we don't have all solutions. Now, I'm going directly from here to Brisbane, but where we'll be getting together, we have a center around Australia. I'm one of the leaders, that FEM center, we talk about waste materials to engineered products, that center. So we're all meeting in Brisbane for that, talk about some innovative solutions. So this is an evolving thing around the world. Don't think that even here is behind. Europe is where all sort of things started. Europe was, we think, far ahead, but then coming back from UK and the time I spent in Greece and all that, I found out, and also talked to a lot of people. They are very keen, they're very, got a lot of incentives, but still early stages. They're not even used some of the waste materials. So what's going to happen, last message, is the future. I didn't even talk about the quantifying things. We have what's called embodied energy of the materials, but the embodied energy of the materials as well as operational energy. Yes, true that we need to look at the whole of life operational energy as well, how it's constructed, how its materials are used. But what's going to happen in the future? Even concrete is, as I said, repeating, the second most used material in the world after water. Concrete is not going to go away. Cement production is not going away, but we have to give the solutions. But by doing that, what is happening in the future is we are working on renewable energy, right? It will come. Now, here we've got all the solar panels, right? Operational energy won't be a major issue because it's all solar power, everything being generated from that. So what is in the future? What's going to happen is the power operation energy side will become renewable anyway, like the environment friendly. But that's why we have to work on what is called embodied energy, low carbon materials. So that side will become even more important. So today it's really very brief. I can talk for a day on this or more than that. But very briefly of the important points of how we are heading towards the low carbon concrete. So we will continue. I say we're happy to take over. Yeah. So and actually I thank the audience here. And also again, we may not have time for questions. Few minutes on questions. Anyone having any questions for discussion? Yes. Yes, that's right. Because people are, for the people who are joining from the webinar side, I had to say that the question is a good question. So the high-strength concrete, we need to make people just work on pace, try to improve all that, but you can, if it breaks to the aggregates. So to make high-strength concrete, essential to look at the aggregates. In Burj Khalifa, they had to import the aggregates. There's another building in Malaysia also. They had to get some special aggregates. Australia, we are lucky. We have very good aggregates. We can't, my problem is in the lab, I can't produce any low-grade, low-strength concrete. Aggregates are too strong. Here, even in here, the aggregates are really pretty good, actually. But some countries, we have very weak aggregates. So yeah, it's good question on that. So we need to get to that, you need to strengthen the aggregates. We are trying also other things like trying to coat the aggregates with graphene oxide or something, some newer things to improve the strength of aggregates. We think may be successful, but again, that it's not been done at the moment. No solutions to improve the aggregate quality or the strength at the moment. So strength of aggregates is the key for high-strength concretes. We got an award for that work, the award, excellence award for that work. It was not that difficult to say that, we know it's happened, but no one had said this before. You see one of the students' papers, long time back, trying to say this message of the breaking through the aggregates, but not many people took notice of it. So now actually, I'm sure people after that was published, I think people start thinking a bit more on the aggregate side. But any other questions? Oh yeah, there's one more question here, which from the webinar side, that's from you, I think. That's not no question. That's not. No, that's not. But yeah, but make sure that actually the people who are in the webinar now, if you like the CPD certificates to other things, now you can really. I think that's very clear. I have to thank Ayesha and Chatumi for inviting me to do this session. And there are two things. One is the Colombo School of Engineering, the first batch of students, I think, here, some here, but also listening from the webinar side to really the first lecture for the CSE, as well as the SDI, Structural Design Institute. Chatumi is actually doing a great job with the CSE. Thank you, Aisha, SDI. You saw the only thing is you got me to talk for 5 hours on SDI today, but that's all right. But that's all right. I was very happy to do that. But while I'm here, I want to just make sure that I put all that time for these things. And thank you for inviting me. And also you got a very good audience as well. But yeah, because very short time, how many days? 1 day or 2 days, got a very good audience. Thank you for the webinar. I think we had a large audience today. I think actually we have still a lot of people in the webinar listening to us. So thank you for listening to me today and everyone coming here. We can, other questions, I suggest that you have some emails for the SDIs and all that, and can send to Ayesha and SDI email, and you can pass those questions to me. I'm happy to answer. So thank you very much. Ah, yes. Yeah, yeah. Yeah. I think you bring a very good point. So I didn't go into that. Thank you for thinking about it. The question to the people you listening to the webinar, I want to say the question is, if you break the glass particles even further, I mentioned it has some cementitious effect, possibly cementitious effect. Same time, the question is whether it will reduce the ASR. Yes, answer is. We found that breaking down to the particles to that level and to really will break down will reduce ASR issue. I got that idea first from again one of my mentors of concrete technology, living mentors at the moment, Dr. Surendra Shah, which I was time 1 month with him in Northwestern University at that time, when just after my PhD. But he's the best in the world in the technology side still. He's actually 85 years. Actually, I can't say I'm going to retire a few years, but because he's 85 years, he's just accepted appointment as the Vice Chancellor's Professor in Texas University. He was in Northwestern. So, but I had a chance to, he's very close to me, had a chance to sit him down next in the bus when we went for the ACI convention in 2019, just before convention. He wanted to just sit next to me. It's such an honor for me. He said, "Can I sit with you and we'll have a discussion?" And I asked on the way from him, "What do you think? I'm doing this work on the." Exactly, he said that at that time, and then now we are finding that answer. It's a very good point. Prayash is doing it, but same time, it is the breaking down to glass to smaller particles. We think the ASR issue will go before. I'm sure there'll be other questions from the audience, but I think we may have to stop there, and I think we will continue this discussion other days.
Thank you so much for joining. And for SDI. We hope all of you have benefited from this. We shall have the Google Forms later. We have already answered that. So you would
it will be safe. And please do keep an eye on our YouTube page and keep an eye on our WhatsApp group as well, because we can make webinars a little more regular. Once a month, so that all is also benefit. And additionally, we do keep an eye on our other events, because we have a lot of interesting events with a lot of people, very knowledgeable people who have a lot of courses, and especially when it comes to how and we have new events with people. So do keep an eye, and if you have any questions, I will or make a message on WhatsApp as well.
Yeah, just one, sorry, Ayesha, I normally don't want to answer a lot of, as I said, some urgent questions, but there's another good question on the chat side. Also, thank you for all the kind comments coming through the chat site. You know, there are so many comments thanking for this event and the talk. So thank you for all the kind comments. Also, I got a saying that, and I've just read one. Thank you, sir. It's a great opportunity for me. I'm also working on the low carbon concrete and enthusiastic in listening to you more in future. And there are many other comments, but thank you for all those comments. But one last one, which I want to answer there, is that on the there's a question to say there was a research about the use of limestone even historically, and as a result, that in the case of cracks and pores, the expansion of its kind of helps as a self-curing concrete. How accurate is that practically? It's a very good point. I'm also interested in some historical concrete. As I said, I had a look at the Roman concretes. Again, I'll leave it to another day, but even some of the mortar used in the bricks and all that around the areas around here, Anuradhapura to other ruins. I'm very interested. I had very good conversation with there's someone from Slit here, but Professor Anavira taught you, I think you said you're from Slit, taught Professor Anavira. I have a lot of time for Professor Anavira, and again, I have a lot of regard when I was even studying as undergrad. Professor Anavira, who is one of the very senior professors here, and now working, used to be Peradine, now in Slit. But so he has also mentioned a lot of things about this whole the concretes around the mortars and all that. Has some limestone, a very good point, I think, coming from the because the direct message, I won't read the name, but it's a good point about limestone. It's been used in old concretes, as well as I said, limestone can be used in cement. However, we need to do a bit more work. The answer is the cracks and pores, all that expansion of that for self-curing. Also, the word is self-healing concrete, that we think limestone can expand and help with the self-healing properties of the cracks in concrete. But no, the answer is not really proven yet. So there's a bit more work had to be done. And there's a danger that we are not doing enough work around the world on some of these innovations and all that. And the cement companies are very bad. I should be saying this. There could be some listening here. But in terms of supporting some of the research, I think we need to, for the concrete, especially manufacturers, the concrete industry, have to be help in some of the innovations and research, and not just leaving it to the academics. And I have to say, exceptionally, CSEC is, as I know, one of the conferences here. CSEC had more papers than the universities here. So CSEC is doing great work on R&D under Mr. Shoma's guidance. So we got the design, the research leaders here, but that's kind of work had to continue, and to have to take it to another level. Thank you. I can talk forever. I keep talking, but thank you. Thank you very much. One last one before everyone goes. Someone talks about geopolymer concrete, whether we should use inorganic geopolymer concrete. I had students, PhD students. It's a good point. One last comment on that: cementless concrete is expensive, and there are some other issues. We have just published the first standard guidelines in Australia. You can have a look at that as well. Yes, geopolymer concrete, but my thinking is geopolymer concrete will come, but we still need to work on our traditional concrete with the cement. Cement is not going to go away. I have worked on geopolymer concrete. I have support from companies, but my thinking is we shouldn't think too much about the cementless concrete. We just should work with the concrete. Even geopolymer concrete we can use, but with some cement as well. So which we can have a bit of a hybrid. So geopolymer concrete we can read a lot, but as a low carbon concrete. But it's really it's going to be, people could be using it, but it has many other issues. Maybe I'll leave it to another day to talk about that, especially with the acidic, some of the acidic attacks and all sort of things, some durability issues to some other curing issues and certain things. But it's a very worthwhile exploring a bit more on geopolymer. So with that note, I think I'll just will stop my talk. Thank you.
Thank you, everyone.